Welcome. In this video, we're going to talk through some key calculations from the copper and brass lab. There are some important questions to answer just about what is happening during the experiment and why we would do certain steps. You should be able to find the answers to these questions up here at the top within the video itself. What's not covered in this video is how to actually go about doing these calculations. So I'll give you some hints on those. And also remember up here at the top, there are some videos that you can use to review the ideas behind molarity. So like, what are solutions? What is molarity? How do you do dilutions? If you want to look in the textbook, the section of the textbook is chapter 4. Section 4 goes over molarity and dilutions. So this should be a review from regular chemistry, but when we need a refresher, it's good to look over those. All right, so let's scroll down here to our first calculation here. I'll give you a hint. So what he does here around minutes like 9 to 13 is he makes a standard solution. So a standard solution is something with a known concentration and known concentration. And what we're going to do in this lab is we're going to compare our known to an unknown, right? Our unknown in this lab is the brass. So we know that the brass has some copper in it. We just don't know how much. So that's our unknown. So we're going to make a solution where we know the concentration of copper and use that as a comparison point. Okay, so that's the purpose of making the known standard. And we want to do a calculation to find the molarity. So this is something that you're going to, record from the screen. And then to find the molarity, just a reminder, molarity is moles per liter. And the way that you find moles is you're going to take your mass that you just record over here, and you're going to convert from grams to moles. And so the molar mass is given to you over here. So you should be able to find your moles of your copper nitrate trihydrate. And then you're going to take those moles and you're going to divide it by liters. So you want to make sure that you convert your milliliters into liters. So we need to know our metric conversion. So 1 liter is 1,000 milliliters. So that's going to be 0.05 liters. So you're going to calculate your moles using the molar mass, divide it by 0.05 liters. That is going to give you your answer in molarity. So that is tip number 1. Then what we do is we take this known solution and we dilute it down. So we're actually going to end up with 5 solutions with known concentrations. And we want to do this so that we can make a nice graph out of it. And the way that we do a dilution calculation is to use this right here, M1V1 equals M2V2. And what that means is the initial molarity times the initial volume equals the final molarity times the final volume. So like if you're going to look over here, at our first one, the initial molarity is going to be whatever you calculated up here. So your answer to this calculation, this right here is M1. This is your initial molarity. And which I don't know what it is right now. You have to calculate it. Okay, so M1 is your initial molarity. And then that's going to stay the same through all these calculations. V1 is your volume of that standard. So M1 is the concentration of the standard. Let's label it this way. And then V1 is going to be the volume of the standard, which is going to vary by which solution you made. So it's either going to be 1 mil, 3 mils, 5 mils, etc. M2 is going to be your unknown. That's what you're trying to figure out. That's what we're trying to solve for. And then your V2 is going to be your final volume, which all of these are diluted to the same final volume. It's 10 milliliters. So the way that we are going to find our diluted concentration, for example, is basically we're going to rearrange this and we're solving for M2. So we take the concentration of the standard, which you will have calculated in the previous step, and then you're going to multiply it by the volume of the standard used, which in this case is 1 milliliter, and then you're going to divide it by the total volume. So notice how basically what we're doing is the new molarity is just going to be 1/10 of whatever the original molarity was. So that's kind of our general pattern here. Down here, it's going to be 3/10 of whatever the original molarity was. Down here, it's going to be 5/10, which is 1/2 of the original molarity. So you just want to calculate what the molarity of all these solutions are. And then later on, near the end of the video, like around minutes 36 to 38, so this is like a significant time later, you're going to then come back to this table and you're going to record the absorbance of each of these solutions. And the purpose of that is once you have this table filled out, you're going to have 5 concentrations with 5 absorbances. So you're going to know the concentration and absorbance for 5 different data points. Using that, you should be able to make a graph. And on this graph, the x-axis is going to be your concentration measured in molarity. Your y-axis is going to be absorbance. And absorbance is actually a unitless number. So that's kind of unusual, but there's actually no unit for absorbance. And then you're going to use your data points and you're going to make a graph. So you're going to figure out, you're going to figure out what your scale should be and all those good things and label your axes with values. Okay, so you're going to make a graph. I'm just kind of sketching one right now as an example. It should look kind of like this. We should have a nice linear graph that intersects at the origin, because when we have no copper, when the solution's clear, we should have no absorbance. This right here is, we should have a 0, 0, should be a point on our graph. And then we're going to find the slope of the graph. And you can find the slope of the graph by doing, you could do it by hand and do kind of like rise over run using 2 points from your line. Or if you want to use your graphing calculator and find the slope that way, I'm fine with that as well. So your slope is your rise over run. So your change in y, over your change in x. And let's say your slope is like, I'm just going to make up a slope. This is from data we collected a few years ago. So your slope for this lab will probably be different. But let's say that you find that your slope is 2.97. So that means if you write an equation for this line, you write as y equals 2.97 times x. And if we think about what the y and the x represents, really what we're saying here is the absorbance is 2.97 times the concentration. And so what we just did here is we used these solutions of known molarity, right? We made solutions, we knew the molarity of them. We measured the absorbance, and we made a graph. And now we have a relationship between the absorbance and the concentration. And then the reason why this is helpful is when we go ahead and measure our unknown, which is our brass, we can now use this equation to solve for concentration. So when we get down here, later on in the lab, I think this happens around minute like 38 or 39. It happens right there at the end. You measure the absorbance of your brass solution. Okay, this is something you will record right up here, absorbance of your brass solution. You're going to get some number there, so you find it in the lab. And you're going to be able to use this absorbance right here combined with this relationship that we just came up with to solve for concentration. So like we could take this equation and rearrange it and say concentration is absorbance divided by 2.97. So if we know the concentration, we can calculate the absorbance, which is very cool. So that's what we're going to do. So you're going to use that absorbance to find the concentration. Actually, the thing I want to mention right now while we're thinking about this is Beer's law. The Beer-Lambert law is written like this. A equals A, B, C. So A is absorbance. And these two things are like constants. It's something called the, I don't have room to write this here, but A is the molar absorptivity, and B is what we call the path length, and they both have to do with your experimental setup. So like what wavelength you're using, how far the light has to travel in your spectrophotometer. So these are something they're going to vary with your experimental setup. And then C right here is the concentration. So if you think about what this Slope, we just found out. What does that represent? The slope of our graph represents the molar absorptivity times the path length. That's what we just found here in terms of this equation. So again, absorbance is some value times the concentration. They're directly proportional. That's the main idea behind Beer's law. Okay, so we will find the concentration by taking the absorbance divided by our slope, right? Absorbance divided by slope. I should clarify, 2.97 is not the slope of your graph. This is my imaginary slope that I just made up, right? So I shouldn't see you using 2.97. I should see you using the slope of your graph that you made based on the data. All right, so once you find the concentration, you can find moles, because if molarity is moles per liter, we can rearrange that and find moles if you do molarity times liters. And then once you know moles, you can use molar mass to find grams. So if we take moles of copper, we can multiply it by the molar mass of copper to find grams of copper. And then once we know grams of copper, our goal is to find the mass percent. So we take our calculated grams of copper and we're going to divide it by, hold on a minute, please. We're going to divide it by the grams of brass, which is the very first, I think it's the very first piece of data we collected way back here at minute 1. And that will give you a mass percent of copper. All right. Thanks for watching. Let me know if you have questions.